All right, welcome back, everybody. Any questions before I continue with chapter 8? Give me 1 second. All right, well, let me continue with where we left off. And I made note that we stopped on slide 9, but I just want to back it up just to make sure you understand where we were. We had just finished talking about polyatomic ions, and those are found on your table, the periodic table, in the left corner of the periodic table. And the point about these is that they come as a unit. They're a single entity. If you need to use more than one, then we put a parentheses with a subscript with whatever number above 1 on the subscript. Notice that every one of these polyatomic ions have a charge. They are ions, though they are made up of, some of them are made up of covalent compounds, nonmetals, but overall, because the nature of the beasts and the way they're put together, is they end up with a charge that is actually distributed throughout that molecule inside, throughout the polyatomic ion. Okay, they each have their own unique name. We don't change the name. So if you have NO3 negative, its name is nitrate. And that's it. We don't change it to nitrogen trioxide or anything of the sort. Anything of that sort. Okay, so we've got it. This is where we ended up. Compounds, and when we start putting them together, have to be neutral. That is, we end up adding enough cations and enough anions to equal 0. And that's 99% of the species that we're going to work with. But that general formula probably is more descriptive. Instead of saying 0, you say the charge of the molecule. Because sometimes you can, you may not, you could figure out the oxidation number of an atom within the polyatomic ion, which has a charge, right? But most of the time it's 0, but you can utilize it to say, no, cations plus anions equal charge of molecule, okay? So here we know they're going to ask you to combine sodium and nitrogen. Well, before you can combine them, the first thing you need to do is put them into ionic form. Okay, and this is where it comes to recognize where they're at on the product table and what group they're in, because that tells us what the charge they will have. And then we go look it up. So we know that sodium's in group 1, so it ends up the +1 charge. And nitrogen, when it becomes ionic, remember we're talking about ionic compounds here, it ends up with a -3 charge. -3 charge, and not only that, the nitrogen, by becoming -3, now we change its name to nitride. Okay. Now at this point, you may not need the name, but be aware of it, because now here in a few slides we will need to know the name. Okay, so we can name it. And so now we see we got 1 plus and 3 negatives. So we have to add enough negatives, enough positives to cancel the -3 of the nitride. So that means we need 3 sodiums, which tells you that coefficient 3 is going to be the subscript for the formula. So the formula is Na subscript 3 N, and its name sodium nitrite. Okay, let's try this one. We just did sodium, so we know that sodium will always have a +1 charge in ionic form. It's a group 1 element. Sulfur is in group 6, and being group 6, being a nonmetal, it will gain 2 electrons because it needs 8 to get that magical 8. And in that process, it now has a -2 oxidation number, and furthermore, its name now becomes sulfide. S is sulfur. Okay. S-2 ionic sulfur is sulfide. All right. So now you can see, like we did with nitrite, we need 2 sodiums to counter the -2 of the sulfide ion. So the formula becomes Na subscript S, subscript 2S. Okay. Magnesium and oxygen. Well, magnesium is in group 2. So ionic magnesium has a +2 charge. Why? Because it's a metal. It's in group 2, having 2 valence electrons. It will lose 2 electrons. Okay. Oxygen is a nonmetal, and just like sulfur is in group 6, therefore will gain 2 electrons. And ionic oxygen now is called oxide. Now the term oxide, sulfide, all the ides for the nonmetals, keep this in mind. Even though we're working with ionic compounds, the name changes to whatever that name is for the anion. We maintain that naming when we're dealing with covalent compounds. Okay, covalent compounds. Now I don't know if I mentioned about the oxidation number. I threw that in there, but with respect to ionic compounds, we know they have a full negative charge, full positive charge. It's a charge. With respect to covalent compounds, they do not have a full negative. They're shared electrons. They have a partial charge. So we really can't use the term charge. So to encompass both ionic and covalent compounds, we talk about oxidation number, which is simply the quote charge that they have, either the number of electrons they lost or gained. All right, so with that being said, we see that magnesium is a +2, oxide is a -2, so we can very simply combine them together as a 1-to-1, okay? Because they cancel each other out with respect to the charge or the oxidation number. Okay, potassium, as with sodium, is in group 1, and therefore ionic sodium will have a +1 charge. Phosphorus, group 5. It needs 3 valence electrons, and it will pick up 3. And so also remember, keeping back in your mind, its new name is now called phosphide. So in this case, we need 3 potassium ions for every phosphide ion. Okay. And so its formula will be K subscript 3P. Okay. Now, this was a little bit more challenging, but let's work it through. We got calcium and nitrogen, which, as you know, will become nitrite. So calcium has a +2 charge. It is a metal, it is in group 2, it will lose those 2 valence electrons. Nitrogen, okay, which is in group 5, again, like in phosphide, will gain 3 electrons, okay? And its name becomes, as I stated earlier, nitrite. Now, in the earlier examples, it was a straightforward, I need 3 of these for 1 of these, okay? Or I need 2 of these for 1 of those, straightforward. But here, it's not straightforward. We have the calcium ion, which is a +2, and a nitrite ion, which is a -3. So we have to combine them such that they cancel. We have enough of each to cancel each other out, okay? But the numbers are not straightforward. So how do we work that? Well, let me ask you a question then. How do I add these 2 numbers, these 2 fractions? What am I looking for when I want to add 1/2 plus 1/3? Okay. Am I not looking for a common factor? Lowest common denominator, right? And normally for small numbers like this, we can just simply multiply the 2 and the 3. And so in this case, the lowest common denominator is 6. All right, so we need to multiply the denominator for 1/2 and the numerator by 3 to give us 3/6, and the other 1/3 by 2 to give us 2/6, right? And so now we can add them together, and the answer is 5/6. 1/2 plus 1/3 is equal to 5/6. And that's how we do with fractions. Well, over here, it's analogous. We have to find a common factor between the two such that they have enough of each to cancel out. And the common factor here is 6. So if I have 3 calciums and if I have 2 nitrites, do I not have a total of +6 for the calcium and a negative total of -6 for the nitrites? And so combining those two, they cancel each other out. And so our formula now becomes Ca subscript 3, because I need 3 calcium ions, and nitrite subscript 2, because I need 2 of them. And so that is our formula. Okay, calcium subscript 3, nitrite subscript 2. All right, aluminum chloride. Aluminum, we know it's a metal, it's in group 3, so therefore it will have a +3 charge. And the chlorides, being in the halide group 7, always have a -1 charge. So we simply add 3 chlorides for every aluminum ion. So its formula becomes AlCl3. Okay. Zinc. Zinc has a +2 charge. And if I can put it on there. Zinc has a +2 charge, and iodide, like the chloride, has a -1. So obviously we need 2 iodides for every zinc ion. And the formula becomes Zni subscript 2. Okay. Now, the metals for 1 through 6 are all have exact oxidation numbers. Those are part of the sweet 16, okay? 100%. Oh, bear with me for 1 second. I'm getting a phone call and I've been waiting. Give me a minute. Okay, sorry about that. It was quite important to answer that call. Okay, so we got number 7 here, which is Cu, copper, and it has Roman numeral 2. Okay, these are the metals that have a variable oxidation state. Therefore, we have to assign them Roman numerals to tell us what charge or what oxidation they have. And in this one, Roman numeral 2 says that we're working with copper +2. Okay, oxygen is a group 2 element, nonmetal. It will pick up 2 electrons and it becomes oxide. And so these two are simply a 1-to-1 relationship, just like magnesium and oxide were up and top here. Okay, so we can very quickly just put them together in the 1-to-1 ratio. Okay, and then here, another example of a polyoxidation number or variable oxidation number, and that is lead. And so we got lead +4. Okay, that's what that Roman numeral means, +4. And then oxygen, which is now oxide, which has a -2. Okay, and so therefore we need 2 oxides to balance the +2 of lead. So its formula, here it is out, is as follows: PbO subscript 2. Okay. Now, with respect to naming, the very first one is sodium sulfide. Okay. Magnesium oxide. Potassium phosphide, calcium, nitride, aluminum, chloride, okay, zinc, zinc iodide. Okay, and so notice here the anion's name has changed. Sulfur becomes sulfide, oxygen to oxide, etc. Okay, the metals we name ways they do not change. Okay, and then we got the last two, which are copper. Okay, now we utilize the Roman numeral here, copper 2 in parentheses oxide, and then lead Roman numeral 4 in parentheses oxide. And note the first 6 metals, we did not use any Roman numerals because they belong to the Sweet 16 category, okay? Because we know they have exact oxidation numbers 100% of the time. Because of that, no Roman numbers are necessary. It is only those metals that have a variable oxidation state that we utilize Roman numerals, okay? Now, you might say, what if I, let's work it backwards. Let's work CuO. We just worked it. We know we're talking about copper 2, but let's say you didn't know what that was, okay? What do you know here? I know that my overall charge for my molecule is 0, okay? I know the oxygen, which is oxide, is a -2. And what I don't know is what copper is. So I generated a very simple algebraic equation, Cu minus 2 equals 0. And if I solve for Cu, guess what? Cu equals +2, which is the oxidation number of the copper we're utilizing. If I would have said Cu2O, and you want to figure out what the oxidation number is for the copper you're utilizing, so you set up very similar. So it's 2Cu, because you got 2 coppers, minus 2 equals 0, okay? And if you solve for copper, guess what? You get a +1. So in this scenario, it is copper Roman numeral 1, okay? So that equation of cations plus anions comes in very handy to figure out the oxidation number of one or the other cation or the anion, okay? Because you're always going to know one or the other. You're going to think of it as 3 variables. Think of it as 3 variables. You know the cation plus the anion equals the charge, the charge of the molecule. You're going to know 2 of those 3 things. So you're going to always be able to figure it out, one or the other, one is missing. Okay, let me clear this up. Charges, okay, add up to 0. Well, formulas with polyatomic ions. Let's try these. So we have Mg, and then you see OH minus. Well, what do? OH minus looks familiar. Well, how do we verify it? We go to the polyatomic ion table, bottom left corner, and OH minus, guess what? It's called the hydroxide, okay? Hydroxide polyatomic ion. And so we got the name in case we need it, and we put it together. And it's like usual, they give you the metal, but it's not in an ionic form, so we write everything into an ionic form. Magnesium has a +2 because we know it's in group 2, has 2 valence electrons, and then we're given the polyatomic ion charge, and that's a -1. Okay, so I need to combine. I need 2 hydroxides. So this is where the parentheses come into play, and I do that. Mg, put them together, parentheses OH and parentheses subscript 2. Once I put them together, don't put the charges up here, okay? Just, that's the whole idea. You put them together, the charges are gone because they've been neutralized with enough of each other to give you end up 0. So that is the formula for magnesium hydroxide, okay? I think it's one of the active ingredients of milk and magnesia, by the way. All right, now let's do another one. And we have the PO4 negative 3. Again, you recognize it as a polyatomic ion. Question is which one? Well, we go to the table. PO4 negative 3 is this one right there. And it has the name of phosphate. Okay, phosphate. So has a negative 3 charge and it has the name phosphate. So as before, we write the ion. So potassium is a +1. We worked on that one before, previous slide. And we got the PO4 negative 3. Okay, that means I need 3 pluses to cancel out the negative 3. It's not necessary to put a parenthesis around potassium, it's just a single element. We can just simply add a 3 in front after the K, subscript 3, and that is the formula for potassium hydroxide. Okay. Silver. Silver is Ag +1. It's one of the sweet 16 constant oxidation number. And then here's the other polyatomic ion, SO4 negative 2, that is called the sulfate. Okay, sulfate. Let me talk about that for a second. Notice here we got S, which is sulfur, the element, the ionic sulfur, which is sulfide. And then we start introducing the ATE and ITE. When that happens, think oxygen bonded to whatever that prefix is. That prefix is SUL, which is sulfur. And so SO4 negative 2 is the sulfate. So you take out the IDE and add the ATE. If it has one less oxygen, SO3 minus 2, it is called the sulfite. Okay, so the ITE, the ATE, think oxygen bonded to whatever the prefix in this case is the sulfur. Notice that nitrogen. We have N, which is nitrogen. N negative 3 is nitride, the ion. And then NO3 negative 1 is the nitrate, ATE. Here we go, ATE, meaning that it's 8, meaning it is oxygen bonded to whatever the prefix is, which is the nitrogen for nitrite. And then if we take off one oxygen, same charge, excuse me, that's it, O2, that is the nitrite. Okay, so 8 deal with oxygen bonded, in this case to nitrogen or sulfur. Also to phosphorus, phosphate, similar conditions. Okay, but when we talk about IDE, and that's where the confusion gets in, IDE, always, it's the single element, whatever that element is. Sulfide, just the sulfur. Nitride, just the nitrogen. Oxide, just the oxygen. Okay. Oh, let me clean my mess here. And so its formula, because Ag is silver is +1, we need 2 silvers to counter the SO4 negative 2. Okay. Calcium. Well, calcium we know is A +2. So until you're comfortable with it, just put everything into ionic form. Calcium +2, nitrate -1. Okay, -1. One way to remember is this, okay, I got a nitrogen here, but then immediately following that, I got oxygen. So that should flag you to say, hey, I either got an 8 or an 8. If there was no oxygen following the nitrogen, then it would be IDE. You see how that works? All right, notice here, sulfur. You might want to say sulfide, but right immediately right next to it, we got oxygen bonded to it. So it's either an 8 or an 8. So you go to the polyatomic table to tell you which one, okay? All right, we need 2 nitrates for every calcium. So we need a parentheses and I need 2 of them. So that's what I write down. So I know what to write in the final formula. So it's Ca parentheses, NO3 and parentheses, subscript 2. Okay. As the case with the previous examples, copper Roman number 2 tells us we're dealing with copper plus 2. Okay. So it's copper plus 2. The carbonate already is a -2. So we can simply put them together on a one-to-one relationship. So its formula is CuCO3. All right. So the point here is when we're dealing with polyatomic ions, remember to use parentheses when we need more than one. If you only need one, just leave it alone, no parentheses. So the names here would be magnesium hydroxide. Okay. Potassium phosphate. Silver sulfate. Calcium nitrate. And then we have copper Roman numeral 2 carbonate. Okay. All right. So these are examples of using polyatomic ions. All right. So now we can work on writing ionic compounds, forming the formulas. Okay. So we need to learn the names. And the name depends on whether the metal is a fixed or variable charge, okay? If it's a fixed charge, we don't need to use Roman numerals, but if it's not, we utilize Roman numerals. So if it's part of the 16, no Roman numerals. Not part of the 16, Roman numerals. All right. So let's do one. Okay. We know this one already. We know, as I talked at length about the anion, how it changes its name. Chlorine becomes the chloride. So in this case, it's a simple sodium chloride. We don't use Roman numerals because sodium is part of the 16. So it's simply sodium chloride. It would be incorrect to say sodium chlorine, okay? Sodium chlorine is not correct because chlorine is the element. Ide is the ion, specifically the anion. All right, so we have KBr, similar situation as sodium chloride. Here we got potassium, and bromine becomes bromine, so this is potassium bromide. Now notice something here. You know, keep in mind all the ones we did. Don't forget, you can do a mix and match here. You're not limited to these. Now you can hook up the magnesium with the phosphate, with the sulfate, with the nitrate, and even with the carbonate. You can do the same thing with potassium and hydroxide, potassium and sulfate, potassium and nitrate, potassium and carbonate. Same thing with silver, et cetera, et cetera. So you can do a lot of mix and match here. You know, you're building your database up with the names of different chemical compounds. All right. You're not limited to what we just give you. You can use any metal and any anion and make a compound. All right, so magnesium, we did this one earlier. Mg, magnesium, we know Mg is magnesium. Oxygen is oxide in its format because it's ionic, okay? So it's magnesium oxide. Right now we're dealing with ionic compounds, but like I mentioned earlier, when we convert over to covalent, the bromide and the oxide continue to keep that name when they're bonded to some central atom, okay? Here we have calcium and then F, which is fluorine, but it's calcium fluoride. Now you might be tempted to think calcium fluorine here, and you might be tempted to think diatomic, but it's not. The fact that there's a calcium first, and you'll find that 99.9% of the time, the formulas are written with the metal first. So we got the metal calcium, right? And then what it follows afterwards is the anion, in this case, the fluoride and not the fluorine. Okay, we got lithium sulfide, okay? And then we have silver fluoride. So up to this point, all the metals do not have Roman numerals because they're all part of the 16. They have exact oxidation numbers, okay? Now, the other aspect to remember here is that there are no prefixes. So it would be incorrect to say calcium difluoride. That would be incorrect, all right? Or dilithium sulfide, that also be incorrect. Unless you're in Star Trek and it's dilithium crystals, but that's another story. Okay. All right. Okay, let's continue. Now for polyatomic ions, okay. What I do is this: when I first started learning these, I'm like, you know, it's kind of confused. It's a little bit of confusing aspect, but I start building up kind of a systematic approach. I can't overemphasize that, in problem solving, that you really got to go at it stepwise. This is true not only here, but I know in my career in research and development, it was true then. And it really helped me out. So I got here this formula, and I'm looking at it the first time, and I'm thinking, okay, I got K. I know that's potassium. And then I got P, and I want to think phosphide. However, right immediately after the phosphorus, or phosphide, is an oxygen. Now, when that occurs, without question, the next thing is I don't have phosphide. I have some kind of a phosphate or a phosphite. And then I need to go to the periodic table and look it up in the table to verify. And that's, use that table a lot. So eventually you get to recognize and see these polyatomic ions and recognize them under different conditions, and they become, you recognize them right away. Okay. So like I said, I got K, which I know is potassium. It's always going to be potassium. And then I'm thinking P coming up next. I'm thinking phosphide, IDE. But the moment I see this next species here, the oxygen, I get rid of that, and it's going to be an 8 of some sort. I know it's phosphorus, so it's going to be phosphate, right? It has to be. If this was sulfur, it would be sulfate. If it was nitrogen, it would be nitrate, okay? And so I got calcium, maybe phosphate. So I go verify the phosphate, on the periodic table, and sure enough, it is PO4 -3. Okay, and then to further verify it, knowing that it's got a -3 charge on that phosphate group, and I got 3 potassiums, and I know each potassium is a +1, then boom, I know that's a phosphate. Okay, so its name, let me clear this up a little bit, is potassium phosphate. All right, now I have a parentheses. Automatically, I have a polyatomic ion of some sort. Okay. The first one, I didn't see a parentheses, so I wasn't too sure. So I went through the steps of finding the element phosphorus and thinking it's phosphide, but then seeing its oxygen bonded next to it. So I'm dealing 8. Over here, I got a parentheses, no question about it. Polyatomic ion, go to the table, find that polyatomic ion, you can find its name. We know Ca is calcium hydroxide. Okay. All right, here we go again with similar to the first one. We got Zn, which is zinc. Okay. And I know that zinc has a +2 because it's one of the sweet 16, constant +2. Then I see sulfur here, and I'm thinking sulfide again. But then I realize, no, right next to it is oxygens. So now I'm dealing with 8 or 8. And to make sure I got 4 oxygens, I go to the table and I find out that I have, it's this one is called sulfate. Zinc sulfate. Again, no Roman numerals, no prefixes like calcium dihydroxide or like zinc sulfur tetraoxide. No, not at all. That SO4 is sulfate, no other name. Okay. Okay, with respect to the variable, well, the question is this. Now here we got to figure it out. And we remember number of anions, cations plus the number of anions, it will equal the charge of the structure of the compound. In this case, they equal 0. Okay. And so I break it down into a algebraic equation. I know that copper has some charge. I don't know which one. But what do I know about the chlorides? The chlorides each have a -1. And there's 2 of them, and each one has a -1 and is equal to 0. The whole thing is equal to 0. Okay. And so I got Cu -2 equals 0. Solve for Cu. Cu is equal to a +2. And so the copper I'm utilizing here is a +2 charge or oxidation number. Therefore, I'm name-wise would be copper, Roman numeral, large uppercase Roman numeral, parentheses, chloride. 2, did I say 2? Roman numeral 2, chloride. Okay. They may ask, well, wait a minute, what do you mean about this equation of provide 0, 1? You can use this for multiple things. Look at this, check this out. Let's do the sulfate. Okay. Let's find out the oxidation number for sulfur under these conditions. All right. So we have sulfur plus oxygen will always have a -2, always. Okay, so we got 4 of them, and each one has a -2, and then the overall charge is a -2. Okay, so I can say S minus 8 equals -2. Okay, sulfur equals 8 minus 2 equals 6, +6. Under these conditions, the sulfur of the sulfate polyatomic ion has a +6 oxidation state. Okay, and that's why I said using the general formula, number of cations plus number of anions equals the formula, the charge of the molecule. that would encompass using, you can calculate the oxidation state of any of the elements, because you're always going to know two of those variables. All right, let's clear this up. So its name would be copper, Roman numeral 2. All right. Okay. All right, here we got another one here. We don't know for sure, but we do know the oxidation number of the oxygen. And so we got Pb. Each oxygen has a -2, but there's two of them. Each one has a -2 charge, and the whole thing equals 0. And so we got Pb minus 4 equals 0. Pb equals plus 4. So under these conditions, lead is in a +4 oxidation state. And therefore, we can say its name would be lead, Roman numeral 1p4, well, and parentheses oxide. Okay. Nickel. The question is, remember, you might ask, well, how do I know if that's a exact oxidation state or not? Remember, there's 16. Group 1, group 2, that's 12. And I gave you aluminum, zinc, silver, and cadmium. Okay, so there's 16. That means that any other metal, regardless of who it is, other than those 16, they have a variable oxidation number. So we need to calculate it. Okay, and the bromine, in this case bromide, always has a -1. There's 3 of them, so we got a -3. And so nickel, under these conditions, must be a +3, because each bromide is a -1. There's 3 of them. It's a total -3. Nickel has to be a +3, excuse me. Okay, and so that is nickel, Roman numeral 3, don't forget the parentheses, bromide. Okay, manganese, sulfate. Here we go. Sulfate has a -2 overall. It's a polyatomic ion. Okay, that means that Mn manganese must be a +2. And so manganese, Roman numeral 2, sulfate. Okay, NO3, polyatomic ion, has a -1 charge. It's the nitrate. Copper here has to be a +1 under these conditions. And this is copper, Roman numeral 1, nitrate. And then we got N. Notice nitrogen all by itself. That's the nitride. Okay, -3. In group 5, nitrogen's in group 5, it picks up 3 electrons, it becomes nitride. That implies that cobalt, CO, has to be a +3. So therefore, its name would be cobalt, Roman numeral 3, nitride. Okay. A little bit more challenging, but let's break it down. Okay. First of all, notice that the formula says Fe iron. There's a subscript in front of iron, which tells you there are 2 of them, 2 irons. Okay. Now let's go look. We got the parentheses here, right there and right there. It's a flag to tell you polyatomic ion. Okay. And you see CO3, you're thinking, okay, what is CO3 in the parentheses? Well, go to the polyatomic periodic table under the polyatomic ion part. CO3, okay, has a -2 charge, and its name, guess what? Carbonate. Okay, carbonate. So now you have 2 bits of information to help you figure this one out. -2. So we know that the CO3 has a -2, and its name is carbonate. Okay, and we got that from knowing that the parentheses here tells me polyatomic ion, and then I went in there to look for the CO3, okay? All right, notice there's 3 of them. 3 of those the carbonate ions. There are 2 irons, and overall is equal to 0. So I got 2, let's create the general formula, algebraic formula. I have 2 irons plus I have 3 -2 carbonates, and that's equal to 0. Okay. 2 irons plus 3 carbonates, each at a -2. So I can rearrange it as follows: -6 equals 0. And there's my algebraic equation. Let's solve for iron. So I can rearrange that, add a +6 to both sides. And I got 6. 2F equals 6. Now I need to get rid of the 2, so I need to divide both sides by 2. That cancels my 1. That means that every iron must be a +3 oxidation state, okay? Because I had 3 of them, they gave me a total of -6 for the anion. I had 2 +3s for the cations, and so my charges equal up to 0. I have a +6 and a total of -6, okay? Which means I got 2 irons and 2 carbonates. So it tells me that I'm working with iron, Roman numeral 3 carbonate. Okay, that Roman numeral 3 came from working this equation here, where I got 2 irons plus 3 -2s from the carbonate equals 0. I solve for iron, so each iron must be a +3, okay? But there's also a little trick. If you notice the subscript for the anion, which is a 3, is the charge for the cation. The subscript for the cation, which is a 2, is the oxidation number for the carbonate, -2. Isn't that interesting? So at a glance, I can tell you what the charge is, what oxidation state the iron is in. But if you're not sure, work it through like we just did, okay? And you end up with iron 3 carbonate. All right, some names here or formulas. You got SR, which is strontium, and you have OH, which is the hydroxide. And so we have its formula. We break down the SR, which is a +2. Okay, it's in group 2, it's a metal. And the hydroxide means each one's a -1. That means I need 2 of them. All right, so its formula is SR parentheses OH in parentheses subscript 2, strontium hydroxide. Okay. The gold, we know that the chlorides each are -1, okay? And there's 3 of them, so I got a total of -3. That means I got a +3 for the gold. So I'm using here gold, Roman numeral 3 chloride. Zinc normally has a +2, and oxygen always has a -2. Okay, so I can very simply put them together in a 1-to-1, and that gives me zinc oxide. The phosphate, here's phosphate, polyatomic ion. I know that the barium is in group 2, that's a +2. The phosphate is a -3. So I need 3 bariums, a common number, which is 6, and I need 2 phosphates, okay, to give me a total of -6 anion and +6 cation. So the formula is Ba subscript parentheses PO4 in parentheses subscript 2 barium phosphate. Okay. Be careful here. This is SO3. You might be tempted to say sulfate. Okay, so you go, you know it's an 8 or an ite. So you go to the periodic table, verify it. You notice that the ite has one less oxygen than the 8, the sulfate. And so this one is called the sulfite. All right, lithium has a +2. And therefore it is LiSO3. All right, sulfur, in this case sulfide, has a -2, and aluminum has a +3. So it's a group 3 element. And so we have another, this time the cation is a greater charge than the anion. I mean, the number, I got a 3 +3 in the metal and a -2 on the non-metal. Okay, but it's still the same thing. We need a common factor, which is 6. So I need two aluminums and 3 sulfites. So our formula is Al2 subscript 2, sulfur subscript 3, and the name is aluminum sulfite. And here they just want to know the name. And so to know the name, we got to know the charge of the polyatomic ion. I know it's polyatomic ion because I've got parentheses here. That's your flag to tell you polyatomic ions. I go look it up. NO3 in the polyatomic ion table has a -1 charge. There are 2 of them, 2 of the nitrates. Okay, that means that copper, this copper must be a +2. Okay. Hence the name, copper Roman numeral 2 nitrate. All right, here they're asked to give the formula, so you might work through those. Okay, here's the following formula: NaNO2 nitrites. Okay, and then the nickel 3 oxide, which is you work it through, you need common number, which is 6, and then magnesium iodide, and then aluminum cyanides. Cyanide is that polyatomic ion. Okay, so work through those so you could come up with the same formula that I have here. Okay, if not, we can bring it on Thursday and we can work it through and talk about it. All right, covalent and molecular compounds. Okay, compounds obviously with only nonmetals. There are no charges here, no ions, and so we are, first of all, we work with oxidation numbers. Okay. Second of all, we use prefixes, and here are the prefixes that we normally use: 1 through 9. 8. Mono, di, tri, tetra, penta, hexa, hepta, and octa. Nano is 9 and deca is 10, but rarely we use those. So we're going to at least do the first 8. Okay. The naming syntax, so format. The name, generally the first element is the central atom. Okay. Now we may give it a prefix if there's more than one central atom. Otherwise, we simply give it the name. So if it's just carbon, 1 carbon, it's just carbon. If it's 2 carbon, we may say dicarbon. Okay, so on and so forth. For the second part is another nonmetal where we may use a prefix and we change the suffix to IDE. So just like in the ionic compounds, oxygen remains oxide, nitrogen remains nitrite, but we do give it a prefix if there's more than one. Okay. All right, so Don't use mono for the first non-metal. So we don't say monocarbon, we just say carbon. Okay. We only use the mono for the second element if there's only one. So CO will be carbon monoxide compared to CO2, which would be carbon dioxide. Okay. All right. All right, so we have CO, so it's carbon. Okay, no name change. Oxygen becomes oxide, and there's two of them, so obviously carbon dioxide. Okay. So here, same thing, carbon all by itself. So carbon, we use a mono, just carbon. There's only one oxide, one oxygen, so that's carbon monoxide. Okay. The way to do this is systematic approach again. Okay, let's do it this way. All right, so we look at the two elements. So the first element is the central atom, and that name is the name of whatever the element is. So this is phosphorus. So I write those names down, the parent name, if you will, and the second parent name, which is oxide, oxygen. Okay. Now I go back and do the prefixes. So there's 2, so there's di, and there's 5, which is penta. Now, that's a prefix penta, but according to the English rules, you can't put 2 vowels together. So we're going to drop the A and be pentoxide, okay? But if you forget to drop the A, I'm not going to make a big deal out of it, okay? So you get like that. You might write it as pentoxide. Correctly, it's pentoxide without the A. When you get 2 vowels together, when you combine the prefix and the parent name, you can't put 2 vowels together, right? Okay. So this one again is P, which is phosphorus, F, which is fluoride. Okay, so the parent name is phosphorus, fluoride. Go back and add the prefixes. You don't need to add a mono for phosphorus. It's all by itself. So just simply phosphorus. There's 3 fluorides, so phosphorus, trifluoride. Okay. Iodine. Iodine is the first element. Okay, it wouldn't be iodide. There's iodine here because we have other things bonded to iodine. So its name is iodine. The 7 fluorides that are bonded are named fluoride. There's 7 of them, and so this name is iodine heptafluoride. Okay, and so here we went with the formula to give the name, but just be able to go the other direction. Okay, given the formula, here we have this one. Well, work backwards, whereas before you said write the parent name, okay, and then come back and do the prefixes, do the same thing here. Okay. The first element is central atom, and that is bromine. Okay, and then the second element is bonded to the central elements. This is oxide. Okay, there's 3, so there's 3 bromides, tribromide, and there's 8. So it's octoxide, so drop the A, octoxide. Okay, tribromine. Let me clear that up here. And like I said, technically that A should be removed. Okay. Similar situation. Write down the parent name. We got phosphorus is the first metal. okay, and then sulfide. All right, and then we add the prefixes. 4, tetra for 4, okay, and hepta for 7. Okay, let me clear this up and let me speed it up a little bit. We'll finish this guy. Sulfur, 3 oxygens, trioxide. Sulfur trioxide. Okay. Now you're given the formula, given, and then write given the name, write the formula, and work it backwards. Figure out the parent elements. So it's iodine and fluoride. So we got iodine and fluoride. Go back and read the prefixes. We got hexa, which is 6. There you go. Okay. Here's the formula. Okay. Same thing. Chlorine. So we got Cl. Oxide, ClO. Okay. Go back and do the prefixes. We got di, which is 2, and pent, which is 5. Okay. That is the formula. And be able to go both directions. You got the formula, give me the name, got the name, give me the formula. And then we got diphosphorus, it's a little tongue twister, tetraiodide. Yeah, gotta drop that A from the tetra. Middle vowels. Reminders, important part, prefixes only for covalent compounds. That's very, very important. Okay, don't mix and match. Ionic compounds do not use prefixes. Okay, Roman numerals are only for those metals and that are not part of the sweet 16. Okay. Roman numerals. And the polyatomic ions, they don't change their name. So the NO3 -1, the nitrate is nitrate. Please don't name it nitrogen trioxide or something like that. Okay, it's nitrate. All right, so you might want to try these for next time. We got barium chloride and nitrogen dioxide, iron 2 phosphate, diiodine, so on and so forth. Here's your formulas or the names, okay? Try those. We'll, if you don't understand it, bring it back to class on Thursday or send me an email. We'll work it through, okay? All right, don't forget the worksheets on this page for this chapter. Practice, 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 like anything else, right? So that, ladies and gentlemen, ends chapter 8. And what I want to do, if there's no questions on this, I want to continue with chapter 9, which deals with acids and bases. Okay, any questions about chapter 8? Okay. All right, well, let's continue with acids and bases. Okay, now the thing about an acid, let me rehash something about hydrogen. Remember, hydrogen, we put that in group 1. And like I stated before, we put that in group 1 simply because it has 1 valence electron on the outermost shell. It's got 1 electron, 1s1. Okay, it's its electron position. Okay, its electron configuration. That's hydrogen. Now, something interesting about the hydrogen atom. Notice that, recall that the s orbit can handle 2 electrons. And so the s can actually pick up an electron. And when it does, it now has 2 electrons. Okay. And because it has room for it in the s orbit, it now has a -1 charge. That's why sometimes hydrogen is put in the group 7 group underneath there, right above fluorine, simply because like everybody, all the halides in that group 7, they pick up 1 electron, so does hydrogen. And this guy is called hydride. Surprising, huh? Hydride, oxygen, oxide, phosphide, nitride, chloride, etc., etc. Okay, the other unique property about hydrogen atom is because it has 1 valence electron, it can easily lose that 1 valence electron. And when it does that, it now has a +1 charge because it's only got a proton. Right here, it's got 1 proton, 1 electron, right? Here, it's got 1 proton, 2 electrons. Over here, it's got 1 proton, 0 electrons. Okay, hence it ends up with a positive charge. Okay, this has a unique name. A hydrogen with a positive charge is called a proton. This is the moiety that causes, that makes something an acid. Okay, anything that when it goes into water and dissolves and breaks up and produces a proton is called an acid. And recall that we had an acid, HCl. Okay, it is a covalent compound. I told you the main difference between an ionic compound and ionic bond and a covalent bond is an anionic bond will dissociate when you put it in water. This dissociate 100% or small percent, but they will dissociate, break up into the ions. The covalent compounds do not, except acids. Acids are the only covalent bonded compounds that when you place in water, they actually dissociate to produce a proton, okay, which makes it classified as an acid. Okay, so hydrogen is very unique. Like I said, it can gain 1 electron or it can lose that 1 electron. So some aspects about an acid is, we all know that, right? Vinegar, lemons, limes, okay, very tasty, very sour, okay? They're actually acids are also very corrosive. And there is, if we were in the lab working on this, there is paper, testing paper, blue litmus paper, has the color blue, that if it's an acid solution, it actually will convert that blue solution, convert it to a red color. And that indicates an acid, okay? Now bases. Bases right now, we're going to use a specific definition, but bases right now are anything that will produce, guess what, guys? A polyatomic ion called the hydroxide. Any species, which basically means that any ionic compound that is placed in water and produces a hydroxide compound is called a base. Okay, so the hydroxy polyatomic ion is what makes it basic in nature. Generally, they're bitter and chalky in the solid form. Okay, they feel soapy and slippery in your finger. If you ever to get anything like, say, Drano or liquid plumber on your finger, it feels slimy. And you might think, oh, it's that chemical. It's not the chemical. It's actually your tissue being broken down. So it does tend to break down protein. That's why you use it in liquid plumber, because a lot of fats and stuff that clog up your drain or fats and long chain hydrocarbon or non-polar species in the drain, and sodium hydroxide does a good job of breaking it up and unplugging your drain. Litmus paper, this is also, we got blue, but we also got red litmus paper. So if you dip it into any solution and that red paper goes to blue, that indicates that you have what's called a base. Okay, doesn't give you the magnitude. It's on an on or off switch. Yeah, that paper tells you you either got a base or you got a acid. We're going to learn that there is a range of acidity and alkalinity. That's what something's alkaline. So if you're drinking alkaline water, you're drinking a base. Okay. Not only that, the alkaline water you drink gets neutralized in your stomach. We'll learn about that here in a bit. All right. So by definition, we're going to have two types of definitions. The first one is called the Arrhenius acid or base definition. And it's real straightforward. Is any species that when placed in water, aqueous solution, and produces a proton, remember the proton, this guy right here, produces a proton, is by definition an acid. Okay. Now we're going to learn that some of these acids are very strong because they dissociate roughly 100%. Strong acids totally break up. We're also going to learn that now some other ones that dissociate maybe 5%. They come in weak, even though they're some in solution, the majority of it is still together and combined. It makes it weak. All right. Now, with respect to a base, an Arrhenius base is any moiety, any ionic compound that when placed in water and produces an hydroxide solution, a hydroxide ion. Okay, this is a proton. This is a hydroxide. That is by definition a base, Arrhenius base. Now we're going to learn here in a bit that this definition was kind of restricted because there's other examples of an acid and a base that, or specifically bases that have nothing to do with hydroxide, but are basic in nature, right? We'll learn about that here in a bit too. All right, so Arrhenius acid, any chemical that produces a proton is an acid, Arrhenius acid. Any chemical that produces a hydroxide ion is a base, okay? So by default, we're talking about aqueous systems only. We're dealing with acids and bases. They're only dealing with aqueous solutions. Okay, and all right. Oh, I got 2:15. Let me stop it here. So we got chapter 9, slide 5. All right, let me stop it here.